Okay, welcome back. For this video, we're going to talk about angular kinematics, especially the angular kinematics formulas. Now, just like with translational motion, once again, we're going to have two types of motion. We're going to have constant velocity and constant acceleration. And remember that we get constant velocity when all of the forces acting on an object are in equilibrium, and we get constant acceleration when all of the forces acting on an object are not in equilibrium. So once again, let's start with the constant angular velocity. Now, the angular velocity is the rate of change of the angular displacement. So first off, what we use to represent angular velocity is this symbol. Now, it's not a W, it's called omega, specifically the lowercase omega. And this equals the angular displacement over time. And you may notice that this is very similar to the translational formula for velocity. So all of the same rules apply. The mathematics is identical. And that is really, really cool if you think about it. Constant angular acceleration. Well, for angular acceleration, we use the symbol alpha. A lot of people like to call this fish, but I call it alpha. And it's going to be the change in angular velocity over our time interval. And again, this should look very similar to our formula for linear or translational acceleration. So mathematically, again, this is going to be identical. All the rules we used for linear motion apply to rotational motion. Now, we can go ahead and start making those other equations. So first off, just to kind of show how this works here, our x's are going to become thetas, the v's are going to become omegas, and the a's are going to become alphas. And the t for time, well, time doesn't change. Time's the same. So, what we can start compiling then is a list. So for our translational or linear quantities, I need to learn how to spell. And rotational. So for linear, we have our delta x over delta t, that's our velocity. And then for our rotational, it's omega equals delta theta over delta t. That's for constant velocity. And then for constant acceleration, we had acceleration equals delta v over delta t. We had our universal equation. I want to use delta t's, not just regular t's. So again, in red, I have the constant velocity. In blue, I have the constant acceleration. So again, these are going to be mathematically identical. And that's basically it. Um, we would still make the same list of knowns and unknowns. What's your initial velocity, what's your final velocity, what's your acceleration, what's your time, what's your displacement. And, using those, we can figure out which kinematics equation we want to use to solve which problem. Um, that's basically it. Now, there is a relationship between linear and angular motion. I call this the bridge. We want to be able to bridge our way between rotational and linear motion. So, for instance, let's say that this right here is a tire. And this tire is, I'll make it clockwise. So the tire is spinning in a negative direction. And there's a little tiny pebble lodged in the tire. Well, if this pebble were to work its way loose, it would follow a straight line path that's tangent. And it would have a tangent or linear speed. And what's kind of cool is if this wheel were turning at a constant angular velocity, if the stone were to come loose at a different position, it would still have the same linear velocity. And we can take a look at things like the radius delta theta. And what we could say then, if this were moving at a constant angular velocity, and this velocity, this tangential or linear velocity would be the same, it'd be constant in a way, a certain way. So we could say that this velocity would be like our delta x over delta t. Well, if we think about our delta x, in this case, our delta x is going to be the arc length. So that means that this velocity actually is arc length s over delta t. Okay, well, we're getting a little closer. We have our definition for the radian. The radian is arc length divided by radius. So that means that arc length s is radius times angular displacement. Okay, I can plug that in then. I can say that this v then equals my delta theta times r divided by delta t. And at this point, you might have already recognized it, but we have a delta theta over delta t. Well, that is the definition of angular velocity, omega. So our bridge between linear and rotational quantities is v equals radius times omega. This is how we can convert between linear and rotational quantities. All we need to know is the radius of the rotating object. I'm not going to write out the derivation, but we have the same thing for acceleration. And the mathematics should work out the same as well. So again, this is a very important way to bridge between rotational quantities and linear quantities. Now, for period and frequency, this is something that might be a little new. The time it takes for the rotating object to make one full circle, so that's 2 pi radians. We call that the period, and we give it the letter capital T. Frequency then measures how many rotations are completed per second. So frequency is how many rotations per second. So what this means then is that frequency is 1 over the period, and the period is 1 over the frequency. They are inversely related. So, think about it. If it takes 1 second to make one rotation, the frequency would be 1. Well, it would be 1 something. The units for frequency are the hertz. The unit for period, that's just going to be the second. Yeah, nothing magical about that. So if an object takes 1 second to complete one rotation, then that means that the frequency would be 1 hertz and the period would be 1 second. And we can do a lot with that. Now we also have something called angular frequency. Going back to our bridge, looking at this means that omega is linear velocity divided by radius. And if we think about our linear velocity, well, our linear velocity, which is delta x over delta t, okay, well, that would be the same thing as our arc length over delta t if we have something moving in a circle. And the arc length is going to be 2 pi radians times the radius over delta t. So remember, s is delta theta times r. So our delta theta is 2 pi since we're making one full rotation. So coming back to this then, omega is going to be 2 pi times r over delta t, and all that is still divided by r. And notice that the r's cancel. So this leaves us with omega equaling 2 pi divided by our time. Now remember, this is the time to make one rotation. That is period. So that's going to be capital T. This right here is what we call the angular frequency. And we call it a frequency because this is something that is divided by the period. Okay? So whenever we have something divided by the period, it has to be called a frequency. Now, I don't want you to get this confused with regular old angular velocity, so that's why I put this tiny little alpha as a subscript. It is different. This is the angular frequency. Remember that frequency is 1 divided by the period. So I can rewrite this angular frequency as such. I can say angular frequency equals 2 pi times f for the frequency as well. Now, just to make things even more confusing, the units of the angular frequency will be radians per second. And we can get away with that because the radian is a unitless quantity. It's a ratio. So the radian isn't really there. So it can get a little confusing. But just remember that if you have anything over the period, it has to be a frequency. So this is going to be our angular frequency. This concludes video 2.